you hear me? Can you hear me? No. Can you all hear me? Put your name in chat. Okay, good. Thank you. Don't forget to put your name in chat. Ooh. Please be sure and put your name in the chat. Can someone tell me why they think I put those two numbers up there? Please put your name in chat. you. As more people come into the room, I'll ask the question again. Any idea why I put those two numbers up on the board? There's no wrong answer here. Why did I put those two numbers on the board? I want people to show it. Please be sure you put your name in chat as you show up. It's almost time to get started. So any question, anybody have any idea why I put those two numbers up on the board? Put a number over there, and a number over there. Please be sure your name is in chat. I have a number of people who put it in a direct message to me, which is fine. But I still need the name in chat. I'm just waiting for more people to show up before I get started. So we don't even have the class here yet. Why did I put those two numbers? I don't even think we have half the class here yet. Well, this is a version of what I used to do when I taught my classroom in high school, and I had an overhead. The first thing I do, I would set the overhead up, or even if it was just already set up, I'd write a number on the overhead. And I asked my students, why did I write that number there? And they threw out all kinds of interesting facts about what they knew about the number. Or I try and figure out what they would like. Like I would have students who try and figure out what's in common to those two numbers, and stuff like that. And the only reason I would write a number on the overhead is so I could focus the overhead. The reason I put a number way over there and way over there is to judge how far I can write to this side over here, and does it show up on the screen? And same thing over here, how far can I write over here, and does it show up on the screen, on the computer screen? That's all. Nothing magic about those two numbers, it's just first two numbers that came to my head. Okay. I'm going to go ahead and get started now. Please make sure your name is in chat for those who are still popping into class. We're going to start with section 4.7, complex zeros and the fundamental theorem of algebra. The fundamental theorem of algebra deals with complex zeros, and it's something I've been mentioning all along about that polynomial functions have complex zeros. Okay. We're going to talk about conjugate pairs, what conjugate pairs are. And before we get to that, I'm going to discuss a little bit about numbers. And then we're going to find polynomial functions with specific zeros. So if we're given what the zeros are, what's the polynomial function that gave us those zeros? Or what polynomial function has those numbers as zeros? And then find the complex zeros of polynomial function. This is the exact same thing we've been doing, except now we'll find numbers that are not real numbers, they're complex numbers. Okay. To start talking about this, I don't know where you are in your math education as far as the different sets of numbers. And I like to go over the different sets of numbers. So I have two rectangles that are up next to each other, but they don't have anything in common other than they're up next to each other. Inside this rectangle, I'm going to do the some sets of numbers, and this is a Venn diagram. And so in this set of numbers, in this subset, we have the set of natural numbers. And this is a stylized N, and it represents the natural numbers. And the natural numbers are the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, on up forever. Okay. And a lot of textbooks now include this as another subset. And it's the whole numbers. And we use a stylized W to represent the set of whole numbers. And the whole numbers are the natural numbers plus 0. So it starts at 0 and then counts 1, 2, 3. On up. So the natural numbers are a subset of the whole numbers. There's only one number difference between the two sets. All right. When I went back to school a long time ago, several of my professors talked about the natural numbers and the natural numbers plus 0. So they didn't talk about the whole numbers, they talked about the natural numbers plus 0, which are two different sets of numbers. The natural numbers and the whole numbers are different sets of numbers. They overlap. That's why the natural numbers is inside the set of whole numbers. Now, the natural numbers and whole numbers are also subsets of another set of numbers. Okay. And that set is the whole numbers and their opposites. As we discussed before, opposites are numbers that combine to 0. And so to get 0 from using 1 is you combine it with -1. So that's going to be -3, -2, -1, 0, 1, 2, 3. All right, and it goes on forever in both directions now, going into the negatives and into the positives. And we call these numbers the integers. I don't know where that word came from, but I know the symbol for integers is a stylized Z. Most textbooks use a stylized Z. Some textbooks use something different. But the Z, the letter Z from my understanding, from a tiny little bit of research I did, the Z is the first letter of a German word for numbers. Okay. Now, if I were to write fractions involving integer numbers, which are rational numbers, which we talked about, we had the theorem of potential rational zeros of a polynomial function. Well, that's another set of numbers here. Well, I don't need the Venn diagram for this because that's another circle, because that's everything out here are fractions of A over B, where B is not 0 and A and B are integers. And we call these rational numbers. Rational numbers. Because a rational number is represented by a fraction or a division. And with division, you get a quotient. So we use a stylized Q to represent the rational numbers. Some textbooks and different authors might use a different symbol for the rational numbers. Now we have two sets of numbers, the rational numbers, which includes the integers, the whole numbers, and natural numbers, right? All three of these can be written as a rational number by putting 1. Okay. And then we have a set of numbers that can't be represented by a fraction of two integers, like the number pi. The number pi is what we call an irrational number. Oops. No. Now, in my mathematical career, the symbol they used for irrational numbers is a stylized pi symbol. Why pi? Because pi is the most famous irrational number. Some other textbooks and some authors use a different symbol for the irrational numbers, but I'm used to using a stylized pi. Now, what we call these sets of numbers together, because they all coexist on the number line, they're right next to each other on the number line, this is what we call the real numbers. And we use a stylized R to represent that set of numbers. Now, there's another set of numbers that includes all of these. It includes all of those, plus some other stuff. And we call these the complex numbers. The complex numbers, we use a stylized C to represent that. And again, some other textbooks and other authors use a different symbol. And I'm not even sure what this textbook uses for these different things. Now, complex numbers deal with numbers that can be written in the form A plus BI. The A portion here is called the real part, official jargon, and the B in this expression is called the imaginary part. Actual term. Now, and the I is pure notation. The I, it represents the number, the square root of -1. Well, the square root of negative numbers don't exist. Yes, they do. They're just not a real number. They're what we call complex numbers. And this is called a pure imaginary number because there's no real part to it. The I is simply notation. All I represents is the square root of -1. If I have a number, let's say 2i, then that is the same as saying 2 times the square root of -1. When I square I get a -1. Right? -1 squared, the square root of, when you square a square root, you're just getting rid of the square root symbol. Well, the square root of -1 does not exist in the real numbers. No, it doesn't. It exists in the complex numbers, which the real numbers are a subset of. Now, how can a real number be written in this form? Well, what if the imaginary part is 0? A and B are real numbers, so this is a real number times I. 2i is a real number times I. This means I took the square root of a -4 to get to I. Because -4, I can write -4 as 4 times a -1, and I can split the square roots up, so that's going to be 4 times the square root of 4 times the square root of -1, which is 2 times the square root of -1. And by notation, the square root of -1 is just I. So if you're taking the square root of a negative number, you can already pull out that negative sign as I. So if I had the square root of -3, I can write that as I times the square root of 3, or the square root of 3 times I. But usually we write the I in front of the square root, so there's no question about where that I belongs. It doesn't belong inside the square root symbol. Now, I kind of got off from how do I write a real number as a complex number when it doesn't have an imaginary part? Well, what's one of the things I always say? We're always adding 0, right? It's just, what does 0 look like? Well, I can write this as, let's do the number 7. I can write 7 as 7 plus 0, and I can say 0, I can multiply I times 0. There, I have it now, I have it in this form. So that's why we consider a real number a subset of the complex numbers, because I can write it as a complex number. So this is just background on because we're going to use some of this information in this section and later on. And you're going to use this if you go on into calculus and other higher mathematics, you're going to need this information. So I'm going to erase this now. Now, what I did about the complex numbers, it should be just a review of what you did in college algebra. Oh, what was the last thing? Oh, find complex zeros. Okay, that's just fact. Now, definition, complex zeros. A variable in a complex number system referred to as a complex variable. A complex polynomial function of degree f is a function in this form. All right, and it looks just like our polynomial functions, where all the coefficients are complex numbers, including the constant, and a sub n isn't 0. Otherwise, we're just dealing with this one, and in that case, that becomes down. And n is non-negative integer, so we have a polynomial function. And X is a complex variable, which means it could be a real number or a complex or more complex number. As before, A sub n is called the leading coefficient. So this is the leading term. And so all the rules for polynomial functions carry over. Everything we did with a polynomial function, we can do with a complex polynomial function. It's just that we have some added things. Now, a complex number R is called a complex zero if f of r equals 0. So that goes in line with the polynomial functions or the real numbers. If r is a real if a real number r is a 0, then f of r equals 0. This is the same thing. Every complex polynomial function f of degree n greater than 1 or equal to it has at least one complex 0. It has a complex 0. Whether it's an even degree polynomial function or an odd degree polynomial function, you will have at least one complex 0. Every complex polynomial function of f of degree n greater than 1 can be factored. All right, so that's not any different than we had before. We can factor it where each thing in here is x minus a 0. It's not necessarily distinct. Well, that's the same as before. That means this r sub 1 could equal r sub 2. So that just means it has a multiplicity greater than 1. And this is just writing them all out. So instead of doing x minus 2 to the third power, you write x minus 2 times x minus 2 times x minus 2. You write them all out. And you will have n number of factors. Whatever the degree of the polynomial is, that's how many factors you'll have. Some of these r's are going to be strictly complex numbers, and some are going to be real numbers. Every complex polynomial of degree n has exactly n complex zeros, some of which may repeat. So if it has n number of factors, it will have n number of zeros, because each factor results in a 0, and each 0 results in a factor. Remember, that's one of those 4 things that are true. If it's a 0, then x minus it is a factor, and it's an x-intercept. Well, that's if it's a real number. In this case, since we're dealing with complex numbers, it may not be an x-intercept. But if that complex number is a real number, then it is also a x-intercept. And the 4th thing, f of that number equals 0, which leads us back to it being a 0. Any questions so far? I know I'm kind of going through this kind of fast, but it'll become more clear when we start working examples of these things. Now, conjugate pairs. If you have a complex 0 of the form ax x plus bi, then you will have a conjugate, then you'll have another one that's a conjugate pair. Okay. So if a plus bi is a 0, then a minus bi is a 0. And we call these conjugate pairs where one is plus the real part plus the imaginary part, and the other one is the real part minus the imaginary part, where A and B are, it's the same A and B. Now, a polynomial function of odd degree means you will have at least one real zero. That goes back to the intermediate value theorem, which if f of A and if A is less than B, and f of A and f of B have opposite signs, then you have at least one zero between those two. And that's what that is same thing works with over the complex numbers. You're getting a real zero. At least one. Now we start using the information they gave us. All right, we have a real degree 5, so n equals 5. And they just want us to find the 2 remaining zeros because they only gave us 3 zeros. So we need 2 other zeros. So 2 is a real number. But 4i is a complex number. So its conjugate pair is negative 4i. 3 plus I is a complex number, and its conjugate pair is 3 minus I. And so here are our 2 remaining zeros. Now, something I noticed in last class, and I obviously didn't have time to change it, is I said it right here. All right, negative 4 is the conjugate, negative 4i is the conjugate of 4i, and 3 minus I is the conjugate of 3 plus I. So those are the 2 remaining zeros. Find a polynomial function of degree 4 whose coefficients are real numbers. Okay, so the coefficients are real numbers. And we have negative 2, 2, and 3 minus I as zeros. Well, it's degree 4, which means we will have 4 zeros. All right, we're missing the conjugate pair here. And so we need to include that one. So we need to include 3 plus 1. And so now we're writing down all of these, x minus c, where c are the zeros. The factor theorem. If f of c is a zero of the function, then x minus c is a factor of the function. So I have 4 zeros. So I have x minus a negative 2 and x minus 2 and x minus 3 minus I and x minus 3 plus I are my 4 factors. However, they don't tell us what the leading coefficient is. Since they didn't tell us what the leading coefficient is, I need to put a variable out here, a, and say this is what it is. F of x equals that. And now I need to simplify this before I start multiplying, which is what they want you to do, because they want you to find the polynomial. This isn't the polynomial. This is the factored form of the polynomial. And so minus the negative is plus the positive. I bring this negative sign in, so that's going to be x minus 3 plus 1. I mean, plus I, excuse me. And this is going to be 3, not 3, Thomas. And this one's going to be x minus 3 minus I. And I forgot the A out here. Any questions on what I've done so far? Any questions about what I've done? Any thoughts on what I've done? All right. With the magic of the associative property means I can go into this where it has 3 terms, and I notice that there's x minus 3 plus and x minus 3 minus. Well, I can group the x minus 3's together. So now I have a single number plus a number and the same single number minus the number. So now I have 2 instances where I have the sum and difference of the same 2 terms. I have the sum and difference of the same 2 terms. When you have that, if you remember from algebra 1, a plus b times a minus b gives you a squared minus b squared, gives you the difference of 2 squares. Well, that's what's happening here. So now I'm going to have a times x squared minus 4, right? X squared, and because if I did the binomial multiplication here, I would get 2x and a minus 2x, which goes to 0, which drops out, leaves me the x squared and minus 4. Same thing would happen over here. So x minus 3 is like the a's here. So that's going to be x minus 3 being squared. And then we're going to subtract the square of I. And I should have written it over here, right? Where I equals the square root of -1 and this I squared equals -1. Well, this I squared is -1, so I'm going to continue this way. So I have a times x squared minus 4 times, and I'm going to go ahead and multiply this out, right? Remember that when you're squaring a binomial, you're multiplying x minus 3 times x minus 3, or you use the shortcut. I square the first term, I multiply the 2 together and double it, and then I square the second term. And this is just minus a -1. And so now this becomes a times x squared minus 4 times x to the second power minus 6x plus 9 plus 1. So now we have a times x squared minus 4 times x squared minus 6x plus 10. Now, there's a number of ways of doing this multiplying. And when I multiply 2 terms times 3 terms or more, I like to do the vertical multiplication where I have x squared minus 4, and then the x squared minus the 6x plus the 10. Please notice how I wrote them down. So I kind of put them in columns because that's what I'm going to do when I'm doing the multiply. I do 4 times each of these terms up here. And so negative 4 times 10 is a negative 40. Negative 4 times a negative 6 is a positive 24x. Did I do that right? Yeah. Okay. And then negative 4 times x squared is a negative 4x squared. And I'm done multiplying by negative 4. And now I move on to multiplying by the x squared. And so I multiply each of these by x squared. X squared times 10 is 10x squared, and I write it under the other x squared term. So I'll have like terms in columns. X squared times a minus 6x is a minus 6x squared. I mean, x cubed, sorry. And then x squared times x is x to the 4th power. And now I wrote my like terms in columns, so then I can just combine them, and I get x to the 4th power minus 6x to the 3rd power plus 6x squared plus 24x minus 40. And I'm still multiplying by a. And so this is what my f of x equals. Boom, that right there. Now they do the same thing, except they do their multiply slightly different than I do, but they still get these same terms, right? They do x squared times x, and then x squared times 6x minus 6x, and x squared times the 10, and then the minus 4 times the x squared, and the minus 4 times the minus x squared, and the minus 4 times the 10. And they get these same things I have here. It's just written in a line. And fortunately, there's only 2 like terms. And when you do the multiply that way, and you write them down in order, these 2 end up being next to each other. You get the same thing. So we're going to look at how they do this, which is pretty much the same way I do. Except, as you know, they don't only show all the steps. And so, yeah, so x minus a negative 1 is x plus 2. I mean, x minus a negative 2 is x plus 2. The x minus the 2. The x minus the 1 they gave us, and x minus the 1 we found, the conjugate pair. And then simplify things. What they did was they went ahead and did this multiply right away. And then they rewrote this, and just they didn't show how they got those, but they got them the same way I did. Multiply in by the negative sign, multiply in by the negative sign, group the x minus 3's together, and so that leaves the plus I here and the minus I there. And then they did the same thing here. They did to get this, they did the same thing here to get what we got there. And so they're following the same path, they're just not showing all the steps along the way. And then they squared this out. And they squared I. And then they combined the 9 and the 1, because minus the negative is plus the positive. And there we have it. They get the same thing I did. Well, no, not yet. Because now they do the multiply. And notice they showed all the multiplies. These first 3 terms are my second row here. And the last three terms is my first row up here. And the only like terms are the 10x squared and the minus 4x squared, which are the two middle terms here, which they combine and get the same thing out. Questions? No. All right, here's a new theorem. Every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors. Irreducible quadratic factors are factors that are not factorable over the real numbers. That means they will have factors involving complex numbers. But now we can factor those complex factors. We can factor those quadratics that are irreducible because we can do it in the complex numbers. Oh yeah, and this theorem isn't new. This theorem we had earlier when we were discussing polynomial functions. It's just now we're not worried about the irreducible quadratics because we can factor them over the complex numbers. Now we factor these things the exact same way we factored the polynomial functions over the real numbers. We do the same thing. We can do the same thing. We can talk about Descartes' rule of signs. We can talk about the potential rational zeros. Because some of the zeros could be real numbers. And so that's what we start looking for. We look for the factors that are real numbers, and then we can find the factors that are complex, that are strictly complex. So the degree is 4, so we'll have 4 zeros, 4 complex zeros. They might be all complex. Half of them could be real and the other half could be complex. Or we don't have it. Okay, since the coefficients are real numbers, Descartes' rule of signs can be used to obtain any information about the real zeros, not the complex zeros, but the real zeros. But from that we can theorize the complex. All right. So if we look at this and we count the sign variations, how many times the sign changes? So we had 1, 2, 3, 4 sign changes. So we have up to 4 zeros, or 2, or none. Right? You subtract 2s until you get down to 1 or 0. And we got down to 0 this time. So that means we have either 4 zeros, 4 real zeros, 2 real zeros, or no real zeros that are positive. And when you put negative x in for x, this is the function we get, and they're all plus. So there's no sign variation, so that tells us that there are no negative real numbers. So the sign doesn't change, it stays positive. And because the leading coefficient, all the coefficients are rational numbers or integer numbers, they're integer numbers, then we can use the rational zero theorem to determine the potential rational zeros. So we look at it was a positive 20 and a positive 2. So the factors of 20 divided by the factors of 2 gives us these sets of potential zeros. Right? But because of Descartes' rule of signs, we're not going to have any negative ones. That means the plus or minus is irrelevant because they all have to be plus. They don't have to be positive. So if we have a real zero that's a rational number, it'll be one, it'll come from these sets of numbers. Questions so far? This is what we just had the test over, right? And they did synthetic division. They started with 1, went to 2, went to 4, and went to 5. 1 gave us a remainder of -20. 2 gave them a remainder of -72, -140. Doing 5 gave them a remainder of 0. So 5 is a 0. And so that means these numbers here are the coefficients and the constant of the first degressed equation. 2x to the third power minus x squared plus 8x minus 4. Which is what we have here. And so we can factor this. So what we look at if we used grouping, I don't have to go back and look at the factors of 4 divided by the factors of 2 and then start doing the synthetic division that way. What I can do is all I need to do is we're going to group these two together. I'm going to group these two together. And I want to factor something out of this pair. Yeah. I can factor x squared out of both of these, and that will leave me 2x minus 1. So that'd be x squared times 2x minus 1. And I can factor 4 out of both of these, and that'll be 4 times 2x minus 1. So now I have I have a factor that are the same in both of these products. So I can factor these out. And that'll give me 2x minus 1 times what's left over, which is the x squared plus 4. Which is what they did here. Now these two will give me zeros, right? 2x minus 1 equals 0, or x squared plus 4 equals 0. This one's quite simple. We add 1 to both sides and then divide by 2. So x equals 1/2. I subtract 4 from both sides, and I have x squared equals a -4. Now I want the square root of a -4. The square root x equals plus or minus the square root of -4. Well, I think I used that as an example earlier. The negative sign comes out as I, and the square root of 4 is 2. The I just represents the square root of -1. -4 can be written as 4 times a -1. And so that can be written as the square root of 4 times the square root of -1, which is 2 times the square root of -1. And notation is -1. I is the same as -1, square root of -1. So here are two zeros. One's negative 2y, and the other one is positive 2y. Here's a 0, 1/2, and we already discovered that 5 was a 0. So that's our 4 zeros. Two of them are real zeros, which falls in line with Descartes' rule of signs, where we can have two real zeros. And that means the other two are going to be complex, which they are. So that gave us a total of 4 zeros. And there they state them there. So in factored form, it's going to be x minus a negative 2i and x minus 2i, and x minus 1/2 and x minus 5. All right, x minus a negative is x plus the positive. There's something missing here. I don't like the fact that they did it this way. Because they boo-booed. When it's written this way, where these are linear terms and the coefficients of each one of these is 1, then what I need out here is what's the leading coefficient. Because x times x times x times x is x to the 4th, not 2x to the 4th. So they're missing the 2 out here. Is that making sense? Because this, what we found was 2x minus 1. Well, here's my leading coefficient. If I divide 2, if I factor the 2 out of this, I get that, and so that 2 has to come up front. And so they were missing that square root of 2 there. I mean, they're missing that 2. Not square root of 2. Any questions on this? This is just doing what we've been doing. We're just adding the complex component to it. Composite functions. Composite functions are an interesting thing, and for a lot of people, they can be confusing. To form a composite function, well, first of all, we need to look at what a composite function is, which is what we do, and then we look at how to make one. And then we also look at the domain of a composite function. So what happens with the domain? The domain of a composite function sometimes is a simple thing, and sometimes it's a little more complicated to find it. We're just going to be using algebra to find those things. There's no new skill. No new skill to use here. We're just applying old skills. Now, the definition of a composite function, given two functions, f and g. The composite function denoted by f composed with g. This is not the word fog. This is a little circle. And mathematicians would die without notation. And mathematicians are inherently lazy. So instead of writing out the word composed with, they decided, let's use a little circle for the phrase composed with. That's like this symbol here. Everybody knows what that symbol is, right? Square root. So instead of writing the square root of 3, we just write that symbol and put a 3 underneath the symbol. That's all this is doing. That's all this is. It's just another notation. And instead of saying, instead of writing the words composed with, we use the little circle and we say the words. We say the words composed with. Just like that radical around the 3 is said, we state it as the square root of 3. And so this is the f composed with g of x. What it means is we're doing f of g of x. So whatever g of x is, we're going to put that expression in place of x in the f function. That's just straight substitution. This is something you've been doing since Algebra 1, actually before Algebra 1. We just have a formal definition here when we're dealing with functions and not just expressions. The domain of f composed with g is the set of all numbers x in the domain of g for which f of x is in the domain of f. Because if f of g takes us to a number that's not in the domain of f, we can't use it. Because I can't use that number here. The next slide is a graphic. It's an image that shows this relationship. The more you understand what's happening with composite functions, the more sense this graph makes, this picture makes. All right, so G takes all of its domain over to here. But not all of its domain is inside, not all of its range is inside the domain of F. That doesn't happen all the time. Sometimes it does, but it doesn't happen all the time. So the portion of the domain of G that takes us into the domain of F then takes us into the range of F, which is a subset of the entire range of F. And so that's what we're looking at. We're looking at the domain of F composed with G are these sets of numbers that takes us to these sets of numbers that we can use to find those numbers. So whatever from the domain of G that takes us into the domain of F are the domain of the composition. So this is the domain of the composition, and it takes us over here to the range of the composition, which is a subset of F, the range of F. So the bottom half, we have the top half here, which is just dealing with G, and the bottom half deals with the composition. And these two sets of arrows are talking about the same sets of numbers. So now we start looking at functions. And we start composing them and looking at what happens. So what they say here is that f composed with g of x is f of g of x. So that means f composed with g of 1 is f of g of 1. So I find g of 1 and I put it into the f function. So g of 1 is 3 times 1 squared, right? 3 times x squared, x is 1, so 3 times 1 squared, which is just 3, so this becomes f of 3. And f of 3 is 5 times 3 minus 1. Which gives us, this is 15 minus 1, which is 14. So this equals 14. Now here we're doing the composition the other way. We're going to start with the f function now. So f g composed with f of x is g of f of x. So g composed with f of 1 equals g of f of 1. So I want to find out what f of 1 is. So that's going to be 5 times 1 minus 1. 5 times 1 is 5, and 5 minus 1 is 4. So this becomes g of 4. And g is 3 times x squared, so this is going to be 3 times 4 squared, which is 48. Right? Because this is 16, and 3 times 16 is 48. And so they, yeah, so they start working it the same way I did here. They wrote it out this way. And then they found g of 1, which is 3. And now they're going to do f of 3, which gives them 14, which is what I got. And this one, they're going to do the same way I did over here. They're going to find f of 1, which was 4, and then do g of 4. And so that's 3 times 4 squared. All right, order please. I still have people doing this. They do this, they multiply before they square. Order of operations. That's 4 squared and then times 3. Because you do the exponent before you do multiply. PEMDAS. And so that gives them 48. So that's why I like writing it this way rather than the way they wrote it, because it's 3 times the number squared. That's 3 times the 16. And so f composed with g of 1 is 14, where g composed with f of 1 gives us 48. Okay. Now in letter C and letter G, you're composing the functions with themselves. So on letter B, f was the inside function because you did that one first and then you did the g. On letter A, the g was the inside function because you did that one first and then you did the f. Here, f is the inside function as well as the outside function. So I'm going to do I'm going to do f of -2 first, and then I'm going to put that number back into f. Right? So I put -2 in for x, and I get a -11. And now I'm going to put -11 back in for x in the f function because I'm doing the f function twice, which gives me a -56. In letter D, they're doing the same thing, but it's going to be with the g function. And I think they're using a different number. No, they're using -2 there as well. Okay, I forgot. And so we do g of -2, which is 3 times -2 squared. -2 squared is 4, and 3 times 4 is 12. And so now I'm going to do g of 12. Well, I'm going to square 12, which is one of the first 16 perfect squares, which is 144. And 144 times 3 is 432. Questions? I'm sure there are questions. All right. Yeah. Find the domain. Well, what we look at the domain. All right, so we look at the domain of the inside function. The inside function is the one you're composing it with. So I'm composing f with g. So the domain of g, which is a polynomial, it's a linear function, so its domain is all real numbers. So I start with the domain of all real numbers for my composite function. And now I'm going to do this. I'm going to put the g function inside the f function. The g function is 3x plus 1. So I'm in place of x, I'm going to put 3x plus 1 in the f function. The f function was x squared plus 2x minus 5. So putting x plus 3 in place of x, this becomes 3x plus 1 being squared. And then 2 plus 2 times 3x plus 1. And then the constant didn't change. We square this. And here we multiply it by 2. Squaring this, we get 9x squared plus 6x plus 1. And then multiplying this by 2, we get 6x plus 2, and then the minus 5. And now we combine like terms. So to get this expression here, you're either going to multiply 3x plus 1 times 3x plus 1. And you get a middle term. Or you use a shortcut, which is the first term squared. You multiply the two together and double it, multiply by 2. And then you square the last term. And then this is just distributive perfect. Now we go through and combine all our like terms. And we get a polynomial function. What's the domain of polynomial functions? All real numbers. Now, doing it the other way, G composed with F, we're going to take the F function, which is x squared plus 2x minus 5, and put it into the G function, replace x with this expression in the G function, which is going to be 3 times that expression plus 1. So I do 3 times this expression, which gives me 3x squared plus 6x minus 15 plus 1. And then I combine like terms. And so that plus minus 15 plus 1 becomes a minus 14. And there's the composition. All right, this is just straight substitution and simplifying. That's all we've been doing here. It's just substitution and simplifying. This is nothing new. It's just the notation is new and what to do with the notation. So again, it's a polynomial function, so the domain is all real numbers. And since f was the inside function, its domain is all real numbers. And so we put that on top of this being all real numbers, it's still going to be just all real numbers. Sometimes there is as a restriction, sometimes there is. Questions here? Because now, what happens if those two functions are rational functions? So you have to deal with fractions. Everybody's favorite thing to do. So here we have the two fractions. So I'm going to write them over here. F is 1 over x plus 4. And the domain here is all x such that x does not equal negative 4. And then the G function is 4 over x minus 3. And that domain is all x such that x cannot equal 3. So G is the inside function, so we start with that restriction. We know x can't be 3 because 3 makes this denominator 0, which makes it undefined. The function does not exist at 3. So I'm going to look at the composition of F composed with G. So that's going to be F of G, which is F of 4 divided by x minus 3. That means in the f function, I'm going to replace this x with 4 divided by x minus 3. So this will become 1 divided by 4 divided by x minus 3 plus 4. Now, the next thing the textbook has you do here, well, I don't know if they do it on this problem, but they do it on several of them, is I don't want a fraction inside a fraction, so I'm going to multiply numerator and denominator by the common denominator. The common denominator is x minus 3. So I'm going to multiply by x minus 3 down here and x minus 3 up here, right? Other than adding 0, you're also always multiplying by 1. X minus 3 over x minus 3. So my numerator is x minus 3, because 1 times x minus 3. Yeah. And so I'm going to multiply each of these. I'm going to multiply this fraction, 4 divided by x minus 3 by x minus 3. And then I'm going to add the plus 4 by x minus 3. Here, these go to 1, so that just leaves me 4 plus 4x minus 12 in the denominator and x minus 3 in the numerator. 4 minus 12 is a negative 8. So that becomes x minus 3 divided by 4x minus 8. Factoring out 4 in the denominator, I get x minus 3 divided by 4 times x minus 2. And this is the composition of f composed with g. I set my numerator, my denominator equal to 0, and that tells me what x value I have to do away with here. So I can add it to, so far my domain was x cannot be 3. And here, my x cannot be 2. So I have to, so my domain here is all real numbers x such that x is not 3 and x is not 2. Now the textbook goes about it using a different pathway. They also use this pathway in a different problem, but in this problem they do it a different way. Right. So first note that the domain of G is that x can't be negative 3, and so that is so 3 is excluded from the domain of the composition, which is what we have done here. And because we can't use negative 4 in f of x, I want to see what numbers 4 over x minus 3 gives me negative 4. And I want to exclude that number. And that's what they're talking about here. So that means g of x cannot equal negative 4, because that's the function we're going to use next. So if g of x gives me negative 4, I can't use that x value, because I can't use negative 4 in f of x. So whatever number x gives g of x gives me negative 4, I can't use it. And so we want to set 4 over x minus 3 equal to equal to negative 4. We're going to set the g function equal to negative 4 to determine what additional values of x need to be excluded, if any. Now, and that's what they do. They set this is g of x, and they set it equal to -4. Multiply both sides by x minus 3. And so you get 4 equals a -4 times x minus 3 using the distributive property. And I think they do a couple of steps here in one move. I would subtract the 12 from both sides and then divide through by -4. They just got down to that x equals 2. So I would have subtracted 12 from both sides and got -8 equals a -4x, and then divide both sides by -4. So that's 2 equals x. So they get x equals 2 gives us -4, so we can't use -2. So they got the same number we did earlier. And so it's excluded from the domain. And so here's the, well, they wrote it slightly different than I did. They put the x equal 2 first, not equal to 2 first, and I put it second. Doesn't matter. Means the same thing. Means that 2 and 3 are excluded from the domain. Any questions here? Anything I went too fast with and I need to go back to? Did everyone completely understand how I dealt with the fraction inside a fraction? You will see this in the homeworks. You will see it possibly on an exam. So dealing with complex fractions, which is what this is, it's a complex fraction. You have a fraction or fractions inside a fraction. You need to be able to deal with those. They get really scary sometimes, especially in upper mathematics. Okay. Now we have these two functions, and they want you to find f composed with g and f composed with itself, and then find the domain of each composite function. So they want you to find the composite functions and find their domains. So I like to find the composite function and then look at their domains, right? Since on letter A, we're doing f composed with g, so whatever the domain is here carries over into the composite. And so where 3 over x minus 2 equals the numbers that are excluded here, those also will carry over. But let's see how they work this. So the domain of f is all real numbers x such that x is not -3. And for g, it's all real numbers x such that x does not equal 2. So for the first letter A, the x not equal to 2 is carried over. And in letter B, because we're only dealing with the function f, the x does not equal -3 carries over into the domain of the composite. And so we start with this one, f composed with g. So we're going to do f on the g function. So we're going to put the g function inside the f function. So we're replacing x in the denominator of the f with 3 divided by x minus 2. Again, like I had done earlier, we're going to multiply numerator and denominator by the common denominator, the fraction of all three terms here. The common denominator is x minus 2, so we multiply the denominator of the fraction, of the big fraction, by x minus 2, and the numerator by the same thing. What I used to say is that you multiply each term by x minus 2. Well, if I multiply this by x minus 2, that just leaves me the 3. Multiplying this 3 by x minus 2 is 3 times x minus 2, and 1 times x minus 2 is just x minus 2. I don't like that they don't show all the steps. And then the distributive property here, and combining like terms. Okay, the distributive property here gives me x minus 6, 3x minus 6, and we still have that 3 we're adding up front. So 3 minus 6 is a negative 3, so that's minus 3 there. And now I set the, and then I can, do they factor? Yes. I would, if I can factor this, factor it. Because now all I need to set is x minus 1 equal to 0. And so that means x cannot equal 1. Because this is telling me that 1 is a 0 of the denominator, which I can't have. So x cannot equal, so my domain here now is all x, all real numbers x, such that x is not equal to 2 and x is not equal to 1. Okay, so excluding the 2 from the domain, and then looking at f at the composition, we note that x cannot equal 1 because it results in division by 0, and so we exclude that one from the domain. And they came up with the same thing. And they put the not equal to 1 first. Any questions here? Yeah. Now, when we do f composed with f, f is 1 over x plus 3. So now we're going to put 1 over x plus 3 in place of x here and get this. So now we're going to multiply each term by x plus 3. The numerator becomes x plus 3. This fraction here becomes just 1. And this number here becomes 3 times x plus 3. That gets rid of the fraction inside the fraction. We use the distributive property. Right? So that gives us 3x plus 9, and 9 plus 1 is 10, so we get 3x plus 10. Now, right now, I would set this equal to 0, 3x plus 10 equals 0. So 3x equals a negative 10, or x equals a negative 10/3. And so my two numbers to exclude, my domain is going to be all x such that x does not equal a negative 10/3 and x does not equal a negative 3. Because negative 3 has to be excluded from the f function, and I can't use it in the f function, so I have to exclude it from the final result. Now, they find the negative 10/3 in the other way by setting x divided by x plus 3 equal to a negative 3. So they find it doing it this way. And they would multiply both sides by x plus 3. And actually, this is how they would do it. They would bring this, they would add 3x to both sides. So we have 3x plus 1 equals a negative 9, or 3x equals a negative 10. And then they divide through by 3 to get a negative 10/3. So they go about it a little different than I would. Okay. And then but they didn't show the process from here to here, which I wish they had. And so there they have the same domain that I had stated. Now, here they want you to do a composition of two functions to see what they equal. If they both equal x, then they both are equal to each other. Right? Transitive property of equality, or the substitution property of equality. If f composed with g of x, if f composed with g of x equals x, and f composed and g composed with f of x equals x, if they both equal x, then they'll equal each other. Is basically what they're saying here. And so you look and see what they are. What happens when you compose them? So going this way, we're going to put the x plus 5/2 in place of x here. So we're going to multiply 2 times x plus 5/2, and then subtract 5. These two go to 1. And so that leaves us x plus 5 minus 5, which is x. So, ta-da, it equals x. Questions? Come on. So nobody's having any issues with this. Okay. Now, you can do a direct message to me if you're having questions. So if you're having issues, you can tell me without letting other people know. Because I don't mention names. I just said somebody said this, or somebody's having a problem with that. So, and sure as whatever, if you're having issues with it, somebody else is going to have issues with it as well. So because that's the nature of things. So now we want to look at G composed with F. So I'm going to put 2x minus 5 in place of x in the denominator, no, in the numerator of the g function. So the g function was x plus 5. So now it's going to be 2x minus 5 plus 5. Well, minus 5 plus 5 is 0. And so that just leaves me 2x over 2. Well, 2 over 2 is 1, so that just leaves me 1x. So lo and behold, it also equals x. So they both equal x, so that means they're equal to each other. So we can conclude that f composed with g of x equals g composed with f of x for any real number. For any real number x, or x any real number. So if I put 3 in for x here, I get 3 back. So if I do g of 3 and I get a number, and then I put that into the f function, I'll get 3. If I put 3 in for x here and I do f of 3, I'll get a number. And then if I do g of that number, I'll get 3 back. Now, here's a different thing. We're looking at trying to find the components of a composite function. They're saying h is a composite function. So which f and g gives us this composite function? Now, I talk about inside functions and outside functions. The inside function is the g function. The outside function is the f function, typically. Okay. So the inside function is usually inside parentheses or under a radical or in the denominator of a fraction. So the inside is g is f of x minus 25, minus 5. What's in here is being raised to the 21st power. So that means f of x is x to the 21st power, and g of x is this expression, 3x squared minus 5. So the function h raises the expression to the 21st power. So I could say that g is that 3x squared minus 5 is being raised to the 21st power. So f of x is x to the 21st power. This is one way of doing it. There could be other ways of doing it. I don't know what it would be. Well, I could say 3x squared is g of x. And f of x is x minus 5 to the 21st power. But it's simpler just to take this entire expression bg. Okay. Another one. Oh, okay. So now they're showing it that it does work that way. I don't always think of this. I think of this a little differently, but they're saying that this is the reciprocal. This is the reciprocal of x plus 3. So the reciprocal function is 1 over x. So I could say f of x is 1 over x, and g is x plus 3. So if f of x is the reciprocal function, 1 over x, and g is x plus 3, then the composition gets us h of x. And my way of saying you look for parentheses. Well, I can put the entire denominator inside parentheses. And so this is my inside function, my g of x. And if I replace that with x, that gives me my f of x, 1 over x. Oh, cool. So this is where we're going to start next time. So if you have any questions for me, ask away. I'm here. Well, we just covered 4.7 and 5.1. So everything up to there, considered 4.7 and 5.1 being assigned. So yes, you need to get all those other assignments done. But as we move forward, you need to start focusing on the assignments we're covering now. Question? 4.7 isn't on there. Okay, I'll look for it. And I will add it in because it should be there, but I don't know why it didn't get added in. Okay. Yeah, I didn't realize 4.7 went in there, so if it never shows up, don't worry about it.